So this is Semantic Web Technologies, lecture number 5, Knowledge Representations, part 2. And this is part 2 of the lecture. And today we will talk about description logic, inference, and reasoning. And for description logics, we first have to talk about the so-called open world assumption. So what is the open world assumption? So if we start modeling in description logics, and we might start with a totally empty ontology, then everything is possible. What we do then is we constrain this ontology iteratively, making it more restrictive as we go. So we say, we state what is not possible, what is forbidden or excluded by refinement. So for example, we say a sheep is something or is an animal, and this animal has legs. So all its limbs are legs. Of course, a sheep has much, much more properties, but we do not have to state this. We can start simply by this definition. So if we ask now, can sheep fly? And we only have the definition that sheep are animal and all the limbs of a sheep are legs, we have no idea whether a sheep can fly. Probably yes. So we must assume, or we have to assume, that it's possible that sheep can fly because we cannot entail the negation from the knowledge base we have here. So in the open world assumption, unless we have the statement or we can infer the statement that sheep cannot fly or can fly, then we have to return don't know, possibly yes. In the real world, it's quite the same. So in the real world, in our daily life, we are used to deal with incomplete information, and we refine our knowledge base inside our brain as we go. When we get new information, then we adapt. So this is also the basic idea for the open world assumption. So in the semantic web, we expect people to extend our own models, but we do not worry in advance how they might extend them. So the open world assumptions always assumes incomplete information by default. Therefore, we can intentionally underspecify our models and allow other people to reuse them and to extend them. So for example, then we can also extend our model by the property that sheep can fly. So quite simple. On the other hand, there is the so-called closed world assumption. And in these closed world systems, there, for everything, a place is required to put something to. So you can't say anything until there's somewhere to say it. So for example, you need to have a slot in frame systems. You need to have a field in object-oriented classes, or you need to have a special column to put your information in a database. So in closed world systems, we state what is possible, and therefore we have to specify all knowledge, because knowledge that is not given will be taken as its negation. So the closed world assumption holds that anything that cannot be shown to be true is false. So no explicit declaration of falsehood is needed there. So therefore, starting with our original knowledge base, in a closed world assumption, we could deduce that sheep can't fly. But in the semantic web, the thing we want to do is, as we said, we want that other people reuse and refine our models and can adapt our models. So therefore, we rely in the semantic web on the open world assumption, although it's much more complicated to deal with knowledge in an open world, but it comes closer to reality. Let me give you an example. So for an open world assumption, the existence of further individuals always is possible if they are not explicitly forbidden or excluded. In the closed world, it is assumed that the knowledge base always contains all individuals. So if there's no knowledge about an individual, this individual doesn't exist. Just take this example. We have here a rather small knowledge base given in description logic. So we say here, Bill has a child and its name is Bob. And Bob is a man. So now the question is, are all children of Bill male? can we deduce that? From that knowledge base in an open world assumption, description logic answers don't know. We have no idea because, yeah, Bill might have other children that we don't know of. So it's possibly yes, but we don't know. In a closed world system, for example, in a prolog system, which is an artificial intelligence system, this would be the entire knowledge base, and therefore the closed world assumption, which holds for the prolog system, would deduce that yes, all children of Bill are male because all children are referred to in the knowledge base. There are no other children. There is no other possibility. For the description logics, we have to refine the knowledge base to make a statement whether all children of Bill are male or not. So, for example, we have to extend our knowledge base with this expression where we say, okay, we have the role child, and if we apply this to our individual Bill, we restrict it and say, okay, Bill has at most one child. So there cannot be another child, and then we can deduce that all children of Bill are male. So you see, to make statements like that and to get an answer, you have to refine your knowledge base. Okay, so this is the open world assumption versus the closed world assumption, and for the semantic web, we have to consider the open world assumption. We will come back to that in the exercises. Okay, but today we wanted to talk about inference problems and entailment for description logic. So what are the problems that we really are considering, that we want to answer with the help of a given knowledge base in general? So in general, the problems of inference are the following. So first of all, of course, we are interested whether our knowledge base as a whole is consistent. So whether the knowledge base makes sense. So we want to prove if the knowledge base is consistent, or on the other hand, if it may be possible that we can entail the bottom element from the knowledge base. Then it's not consistent. And what we do for the entire knowledge base, we can also do for a single class. We can ask, is a class definition consistent, or must the class be empty because the definition is wrong? And on the other hand, we also can ask, does a class inclusion, this subsumption, C is part of D, does that hold or does it not hold? And also we can ask about class equivalence. Is C equal to D? So are two classes really the same? And if you compare two classes, it might also be possible that these two classes are disjunctive. It means that no individual is at the same time in class C and in class D, and we can ask for that. Are these two classes disjunctive? Would make sense, for example, if you consider the classes male and female, and then you ask, are these two classes really disjunctive? Class membership is an individual A really contained in class C. This might also be interesting. And another thing that we might ask is so-called instance generation. This is a retrieval problem, which means find all X with the property or with the condition C of X. It means find all X that are in the class C. So for example, find all known individuals of class C. This is a retrieval problem. Yeah. All it comes up then, or is a problem of so-called decidability. So all these inference problems that we have must be solved in a finite time. And they must be so-called decidable. And for description logics, of course, they are fragments of first-order logic. Therefore, in principle, we can apply all these algorithms we already know. We can apply resolution, we can apply the Tableau algorithm, but the problem with them is if we apply on description logics the algorithms from first-order logic, then possibly they do not always terminate, because for first-order logic, we know that first-order logic is only semi-decidable, because there some algorithms might not terminate, and we do not know if they terminate. So the problem is for description logics, we have to find algorithms that always terminate, and there might be no naive solution. So what we do is we have to adapt, of course, these algorithms from first-order logic to apply them on description logic and to maintain then the property that they will terminate and therefore are decidable. So what we do, we adapt the first-order logic inference algorithms to the properties of description logics. And in the course of this lecture, we will restrict only to ALC Tableau algorithm and not to the more complicated Schoen-D or Schroik-D algorithms because we don't have the time for that. But in principle, it works in the same way. So with the Tableau algorithm, you know that also for resolution, we show the unsatisfiability of a knowledge base or of a theory. Therefore, what we do is we try to make an adaptation of the entailment problems to the detection of contradictions in knowledge bases. It means that we try to prove the unsatisfiability of a knowledge base. And all these inference problems that you have seen some slides ago, we have to transform them in a way that we can prove the unsatisfiability or the detection of contradictions based on the problem we are considering. So what we want to do is we want to try to reduce the problems for the knowledge base to unsatisfiability. So let's first consider the class consistency. Here it's the class inconsistency. We can do this, for example, then if we check if the existing knowledge base combined with an instantiation of the class is unsatisfiable. And this, of course, can be checked with a Tableau algorithm or an adapted resolution algorithm. Class inclusion, it's the same way. Let's consider C is the subclass of D. We can rewrite this, of course, with the negation of that. So what we hear is nothing else but we try to combine the existing knowledge base with a negation of this expression, which computes to this conjunction, and we instantiate it with an individual A, and we ask if this is unsatisfiable. Class equivalence it's quite easy because for class equivalence, on the one hand, we have to prove class inclusion from one side and then class inclusion from the other side. So here you have to double check this unsatisfiability. Then for class disjunctiveness, if two classes are disjunct, then of course the intersection of these two classes must be empty. And therefore, you can ask whether the existing knowledge base combined with the intersection of these two classes instantiated with a new individual, which should not exist, is unsatisfiable. Quite simple. And on the other hand, class membership, there you just ask if the knowledge base combined with the negated class membership of a new individual A or of the individual A where you want to check the class membership is unsatisfiable. And in the end, the instance generation or the retrieval problem find all X that are in class X. Therefore, you have to do for all individuals, you have to check whether they are member of the class C or not. So quite simple, check class membership for all individuals. Of course, the question here is it really efficient or is it not efficient? So if we consider our principal problems that we have to transform them to an unsatisfiability problem to be able to apply the automatic entailment algorithms that we have to adapt and to apply the resolution algorithm or the Tableau algorithm. This is based, of course, on unsatisfiability, and we have to prove that there is a contradiction. Therefore, we have to transform these problems, and you can check all these transformations that I have shown you in the exercises and the homework. So in the next part of the lecture, we want to take a look at the Tableau algorithm for the description logic ALC.